Hello, hello, hello. Hello, welcome all of you for this fifth Aveek Guha lecture. Aveek Guha was born in 1973 to Subhendu and Jayashree Guha. Dr. Subhendu Guha was a scientist at TIFR, Mumbai, and Aveek grew up here at this TIFR housing colony, Kolaba. The family moved to United States in 1982, and Avi got his bachelor's degree in electrical engineering from University of Michigan and MBA from Ross Business School at the same university. And he worked for the SAP Americas, then Booz and Company, and most recently at MJ Holding Company as a head of the global strategy and investment. Now, he was founder of MBA DICAMP located in Chicago, Unfortunately, Aveek passed away on March 27, 2016, leaving behind his parents, wife Jessica, and two daughters, Zoe and Lila. And his father has and his parents have given us this amount to basically hold this lecture series in his own memory. So now I request Professor Vahia, who is the president of TIFR Alumni Association, to give his address.
Thank you very much. It's always a pleasure to be in TIFR Lecture Theatre. So we are going to have TIFR Alumni Association, of course, is anybody who has spent 2 years in TIFR is eligible for it, and we now have about 1,000 members. And we of course arrange free lectures and we arrange other programs. So, for example, next Thursday on 22nd May, we have another function here where we will release a book on TIFR's trees, which in many ways are very unique trees, and we'll have a book which we'll release next Thursday. Today, we have Apurva Khare. The formal introduction will be given by Prabhuji. But Apurva, for those who are from astronomy or physics, his mother was also a very distinguished astronomer, Pushpa Khare. And he himself was a mathematics Olympiad student who used to come here quite regularly, but chose not to do PhD with us. I don't know why. That's our loss. So it's a great pleasure having him here. Before I give the mic to Prabhuji for formal introduction, I just want to say that I think if you like the Alumni Association events, please join is one issue. Second issue is you should thank Professor Prabhu, who organizes everything here. And I just come here to collect credit every now and then. So with those few words, let me invite Prabhu to introduce the speaker formally. And then
thank you, Professor Vahia, for all the kind words. But I don't. I mean, he has been extremely helpful and very much supportive for all this. And also, we should thank Snehal, who has been working backbone of our thing. So, and also Kishore Menon, who could not be here because of some family issue. But definitely for the next program that we have from TIFR, which is the Book of Trees that we are going to basically publish it here. So that will be on 22nd May. So I again take this opportunity to invite you for that next week, next Thursday. Please mark it in your calendar. You will also get a very formal announcement of that. So with this, let me start with a very formal thing. So it's a privilege to welcome you all for the 5th Aveek Guha Memorial Lecture. This distinguished lecture series was instituted through the generous endowment from Dr. Subhendu Guha, a former academician at the Tata Institute of Fundamental Research. And we are very grateful for his vision and continued support in promoting public engagement with science and scholarship. The inaugural lecture in this series was held on 28 November 2019 with Dr. Shri Kumar Banerjee, delivering a compelling talk on the complementarity between solar and nuclear energy. Since then, the series has evolved into a platform that spans a wide range of pressing and intellectually rich topics, from the scientific inquiry to economic policy and social equity. So past speakers have included Dr. Shri Kumar Banerjee on energy, solar and nuclear, Dr. Viral Acharya on finance and monetary policy, Dr. Mithun Alur on social justice and inclusive opportunity, and Professor Sudhir Jain last year on the evolving role of alumni. About the TIFR Alumni Association, it was formally established on April 29, 2000, and we are proud to be celebrating our 25th anniversary this year. Over this quarter century, we have grown from an initial membership of just 105 to a thriving network of over 1,000 members. And beyond numerical growth, we have also achieved several important milestones and registration with the Registrar of Societies and the Charity Commissioner, and most notably securing Section 12A certification, which actually grants us an exemption from income tax. So this has been achieved last year, and this is a testament to the dedication of our entirely volunteer-driven team. Now today, Professor Khare will speak on when can symmetries in a group have lengths. So it's going to be a very fascinating thing. And public lectures serve as an essential conduit between academia and society at large. As a publicly funded institution, TIFR bears a responsibility not only to advance scientific knowledge, but also to demystify it and to foster curiosity and critical thinking among members of the broader public. So our vision for this lecture series reflects that commitment. and it is confined to pure science or technology, but also embraces a holistic exploration of ideas that shape our world. Now, it now gives me a great pleasure to introduce our speaker today evening, Professor Apurva Khare. So, Professor Khare completed his schooling in Odisha and went on to earn his PhD from the University of Chicago, one of the world's premier institutions. His academic journey includes working at University of California, Riverside, Yale University, and Stanford University, following which he returned to India. Among the many honors he has received are the Swarna Jayanti Fellowship, the Ramanujan Fellowship, the Shanti Swarup Bhatnagar Prize, one of the highest scientific accolades in India. And he's also a fellow of the Indian Academy of Sciences and the author of numerous impactful research papers in mathematics. He has also a book to his credit. And in today's lecture, Professor Khare will share the fascinating story of how complex mathematical problem was completely solved by a group of mathematicians who never met in person, collaborating entirely through online platforms. A very timely reflection on the evolving nature of intellectual collaboration in this digital age. So, with that, I request Professor Vahia to welcome Professor Khare with the memento. It's a small thing from us. For thank you for coming. Yeah. A very nice book. So, welcome, Professor Khare. It's all yours.
Okay, I think, yeah, you can hear me. Okay, so first of all, yeah. So, yeah, thank you very much to Professor Vahia, Professor Prabhu, to the Alumni Association for some really warm welcome. I've been here since, as I was telling them, since 1998 was the first time I think I came to TIFR, and I've been here 98, 99, 2000, and then over the years again as a student, as a postdoc, as a faculty member, and now somehow in all these years, in the last 27 years, I've never been to this room until today. Because all our lectures as a student would happen on the other, across the corridor in those smaller rooms, and as a nurture program student and so on. Even the seminars I attended and later the talks I gave were all on the other side. But so this is my first time here. Interestingly, on this side of the dais, not that. So that was, but anyway, I'm very happy to be back at TIFR once again. And hopefully when I get some time today evening, I'll sit by the rocks again and, like as I used to do all the way since 1998. That thing you can't replicate anywhere. And okay, so to get back to the topic at hand today, when can symmetries in the group have lengths? So first let me, this is supposed to be meant to be like a general science talk. So I will try to, I'll stick to the slides mostly, but I'll ask some simpler questions as well on this side. And so as Professor Prabhu mentioned, this is the story of how one particular problem question, very simple to state question in, let's say, college level mathematics maybe. The first thing one sees in the college program in math, very simple to state question about such objects got solved. And it is the story as much of the solution of that problem as the process of discovery and the mode of discovery. And it all got solved, as they told you, online on the blog of a famous mathematician, Terence. And so I will also be telling you not just what steps in the progress got made, but at what time they got made. Because this whole thing is based on the question that I had thought of and couldn't find an answer to for 2-3 years. And then Terence put it on his blog, and then it got solved in 5 days. So it's very modern day approach to doing mathematics. And with that, maybe we should start. Okay, so so this is where I should be. Yes. Yeah. So starting from the broader sciences, especially in say lab-based sciences, there's this obvious tradition and long-standing history of very highly collaborative research projects. So here is one from the biological sciences, the Genome Project. Oh, sorry, this is correct. This is right. Yeah. Yeah. So and so if you see the paper in Nature where the final thing appeared, it has 200 plus authors, and some of them are actually not human beings but the entire institutions. Right? So it's really highly collaborative. The similar thing for particle physics, the Higgs boson, 3,000 plus authors in physics letters B. This is, yeah, again, this millennium, right? Even more recently, from astrophysics, from small scale to large scale physics, you have the gravitational waves paper. I took a look at the archive version. I didn't see this one, but I took a look at the archive version, and that had 100 plus institutions. Overall, apparently 800 plus authors. I didn't count 800. I estimated it probably. I was not going to count 800 names. So mathematics as a discipline has, of course, lagged behind. We, in fact, first of all, we are highly theoretical. And so we largely see somebody sitting at their desk and working out stuff. And this is not just now, it goes back all the way to Newton and Leibniz, and sitting at their own desks and doing calculus. Fermat, who wrote down things in the margin or did not write down things in the margin. Gauss, Galois, and so on. Galois' work was not even understood by anybody else even after he died, until for many years after he died. And then finally people started to understand it, and that is the foundations of what people now call group theory. So, and that is exactly what this talk is about. So Ramanujan, of course, coming to India, Ramanujan famously worked alone. And let's see, Andrew Wiles. So 3 decades ago, maybe Andrew Wiles worked secretly for many years to prove this 400-year-old conjecture. That was 30 years ago. 20 years ago, Perelman worked in isolation to prove these 2 amazing conjectures, and then refused both a Fields Medal and $1 million because he did not want any of that fame and money. He just was happy with proving it. And 10 years ago, or in the last decade, Yitang Zhang worked by himself to prove some very famous question, to answer some very famous question which was unsolved and which can be asked to a high school student. Can there be prime numbers that differ by a small margin, like 3 and 5 differ by 2, or 13 and 17 differ by 4? So that kind of thing. Okay. So there are, so very famous problems, very important work in mathematics has happened. And these are just the sort of the most famous examples, but by and large, mathematicians work alone. Or maybe 2 people work, or maybe 3 people work. Certainly 800 people do not work together, like we saw earlier. And this will keep happening. The traditional model is still the only model we sort of are used to. So today, what I will tell you about is a problem that got solved. I will tell you about the problem itself, but I will also tell you about the mechanism, the collaboration mechanism by which it got solved. And that is sort of a very modern day mechanism. It's very atypical for mathematics, but this being one of the few success stories, it's worth telling and hoping that it gets replicated more often. Okay, so the problem is about groups. So groups are known to many people outside of mathematics as well. I mean, the group of rotations in the plane, this is a very standard think of rotations. So what is a group? A group is a set of symmetries. Fundamentally, you think of a group as a set of symmetries. Okay? So for example, you can talk of the water molecule having some symmetry like that, or this is probably ethane, C2H6, right? Yeah, CH4 is methane, C2H6. I remember something from class 11. They have some symmetries as well. But yeah, so inherently, you have some system, you have some set of things or some system, and you have some transformations of that system that preserve the entire system, but can change points or molecules or atoms or things within the system. Those are basically what we call symmetries. Other people might call these as permutations. Okay? So symmetries, permutations, bijections, there are different names. Yeah, Rupek, Namanek, whatever. So the group of rotations, what does it preserve? Again, you can think of it preserving the whole plane. Inside the plane, you take some vector, you rotate it by 30 degrees, you get some other vector, it sits inside the whole plane. So the plane, when you rotate it, stays the same infinite plane, right? But I could also just think of the circle, and I say, look at all the points on the circle, and if I rotate, then the points on the circle stay the same. The overall set of points stays the same, but the points move among themselves. So it's still what I call a symmetry. A symmetry is something that preserves the entire system as a whole, but can switch things around within the system. Well, but the symmetries are well known to people in physics. Of course, there's the Lorentz group of symmetries, just to name one group. Of course, you guys know many more groups. If you talk about a matrix, then it has eigenvalues and eigenvectors, and you can talk about the set of vectors itself. And so that is one symmetry, that is one group of symmetries that I want to mention here. So if you just think of this plane, the blackboard is a plane, then every vector that I draw is a symmetry. What does that mean? It's just a vector. How is it a symmetry? How is it transforming the plane? It's a symmetry because what this does is, if I have a vector V, it sends, so I call this the transformation corresponding to V, and this transformation literally just takes a vector W to V plus W. So it's just addition or translation by V. So this vector here would go here. This vector, the origin, the zero vector here would go to V. This vector here would go here. So each of these is a symmetry of the plane because it preserves the plane as a whole. But it takes individual points in the plane to different points in the plane. It takes this point to this point. So that's why I said that the space of vectors is a group. And of course, similarly, you can take the set, just some finite set, red, green, blue, 3 colors, and you can just juggle them around. And that gives you a permutation. And that's a symmetry as well. So these are all examples of symmetries or groups. Okay. So that is one part of the title, I guess, symmetries. And now what can you do when you have two symmetries? If I have two rotations, what can I do? I can take one rotation and then another rotation. So I can compose two symmetries. I can translate, I can move everything, I can shift everything by this vector, and then I can shift everything by some other vector. So again, I can compose two symmetries. I can compose them in two different ways. I can first apply the first symmetry, then the second, or apply the second symmetry, then the first. Overall, my system as a whole stays the same. The particles can move around in the system, and they move around in two different ways, a priori. So alpha, beta, and beta. I can also reverse. If I rotate by 30 degrees, I can unrotate by 30 degrees, which means if I'm rotating clockwise by 30, I can do counterclockwise by 30. Right? So that's the alpha inverse. That's the notation we use for the inverse transformation, which undoes the change. And if I first do something and then undo the same thing, what I get back is the original system. That is also a symmetry, the symmetry where you do nothing. So it fixes every point in the system, not just the system as a whole. That's called the identity or the identity symmetry or the identity element of any group. So it's the same name, same concept. Now, if I do the first bullet point, alpha, beta, and beta, alpha, do I always get the same answer? So clearly, if you do it, if I first if I add one vector and then I add another vector, versus if I added the other vector and then this vector first. Vector addition is what we call commutative. It doesn't matter in which way you add vectors, you will get to the same thing. So translating by different vectors in either order gives you the same thing. But in general, this is not true. For example, you can multiply vectors in the plane by some invertible matrix, if you know what matrix multiplication is. And then you can say that if I do two such transformations, I don't necessarily get the same answer if I do them in either order. And you can just verify literally by multiplying two matrices in different ways, in two different ways, that you get two different matrices. Fine. So, so a group is said to be abelian, a set of symmetries, a group of symmetries is said to be abelian. If first of all, if you compose two symmetries in the group, you get another symmetry in the group. So it's closed under composing. It's closed under inverting, if you can undo the symmetry. And whenever you compose two symmetries in different ways, you get the same answer. That's called an abelian group. Fine. Now, this thing I'm going to write, so this is the first time we'll do something non-trivial. We will move the symbols on the right-hand side here to the left-hand side. So the point is, you can compose things, then you can also undo things. If I multiplied both here by alpha inverse and alpha inverse, then alpha inverse would cancel away, because if you do something and undo the same thing, you're doing nothing. And here you would get alpha inverse equals beta. And then I can multiply the beta inverse and I get exactly this equation. Okay? So this is just standard group theory language. Two elements in the group commute if and only if this thing is the identity. This quantity is it has a name. It's called the commutator of these two elements, alpha and beta. And the point is, it is trivial. It is the trivial symmetry, the identity symmetry. If and only if these two symmetries can be applied in either order and give you the same answer. That's just the way the equation works out. That's the laws of group theory. Right? So that was one. Okay, so fine. So now we get to the other player in the title of the talk, the norm. So first of all, the norm of the vector, we all know what norms are. The norms are what they are in the picture. Right? So the norm of a vector, a norm of an arrow, is the literally length from the head to the tail, or tail to the head. Yeah. And we will denote it by the usual way we denote norms of a vector in the plane. So what are the properties it satisfies? For every vector, its length is positive, except the zero vector, who's the dot at the origin, whose length is 0. Everything else, no matter what direction, has a positive length. It's like, think of displacement, not distance, which is a vector, but the displacement. That is positive. Okay? Also, also, of course, there are two other things. One is that the length function satisfies something called a triangle inequality. The distance, the length of one side of a triangle is at the most equal to the sum of the other two sides, any side of a triangle. And the third thing is the key point that makes this length function special and makes it what we call the norm. It is invariant under scaling. So if I take 2 times the length, if I take 2 times the arrow, I get 2 times the length. If I take 3 times the arrow, I get 3 times the length. If I take any integer times the arrow, I get integer times the length. So that's what a norm is. So now what we want to talk about today is, when can a group have a norm? So this is fine. The plane, the blackboard, every vector on the blackboard has a norm. You define the origin here, you measure the length from here to here by some fixed scale or some fixed ruler, and that is your norm. But when can a group, a general symmetry group, have a norm? So first of all, what does it mean to be a norm? So here is the formal definition. A norm is simply a same kind of idea. It's a function that takes every symmetry. Think of, like, for example, this is a group of symmetries, vectors. It takes every vector to a number. That's the first line. So now we do the same thing. It takes every symmetry to a number. Okay. What are the properties? The property should be that, first of all, if the symmetry is not the identity, not the trivial symmetry, the length should be positive. Just like if the origin, if the vector is not just the zero vector, then if the symmetry, the translation is positive. Secondly, this thing says that if I apply the red symmetry first, translation by the red guy, and then translation by the blue guy next, together, that's the right, if you apply that together, that's the translation by the black guy. The length of that black guy should be less than the length of the red guy plus the length of the blue guy. So that's exactly the triangle inequality. That's the second bullet point. And the third is exactly the property of the scaling part. If I apply the same translation n times, I should get n times the length. So that if I remember what vectors were, vector is just an object, but the symmetry that it stood for was to translate, to move everything by that vector. So if I move everything by twice the vector, that transformation's length is 2 times the length of moving it by once that much vector. So that's the third bullet point. So it's the exact same things as above, written for lengths, written for symmetries in the group. That's all. So I don't want to write alpha plus beta like we would write a vector plus vector. I would write alpha composed with beta because we compose symmetries. Fine. And here is an example. So example of a length on the vector is R2, all vectors in the plane, and we just think of vectors as symmetries because they are translations. And this is has the usual length function. We know how to measure lengths by Pythagoras theorem, x square plus y square square root. Right? And this group is also abelian, meaning if you add, which we said here, if I add vectors in different ways in either order, I get the same answer. Okay? So, so what I was saying was basically that. So example of a group with a norm, which is R2 or R3, or in general, I can write down Rn. Any n-dimensional space with the usual Pythagoras norm, or there are other norms you can put on this space called the L1 norm or the LP norms. But these are the groups. And the group, of course, the group operation is to add some vectors. Yeah. That's one example of a group with a norm. But the point is, this group, when under addition, is abelian. Meaning that if you add 2 vectors in either order, you get the same answer. The question that I had was, does there exist a non-abelian group with a norm? So for example, can you put a norm on the set of 2 by 2 matrices which have non-zero determinant? Those are also symmetries. They move every vector in the plane to something else. Or can you put a can you put a norm on the set of rotations in the plane? But of course, rotations in the plane are abelian. So that's not what I really want. Right? But more generally, rotation can be given by a 2 by 2 matrix with non-zero determinant. So on that part, can you put a norm? That's not my question. On the entire set of 2 by 2 matrices with non-zero determinant, can you put a norm? Or on a general symmetry group, can you put a norm? And the group should be non-abelian, because for abelian we have some examples. So I wanted an example from non-abelian groups. So I came to this question because of some work in probability theory which I was doing for non-abelian some things. I will call them semi-groups. But then afterwards, when I came to this question in 2015, I started emailing many people about this question. That okay, can you give me a single example of a group which is at once not abelian, but it has this norm property. There is some function, there is some way to measure the length of every symmetry such that the triangle inequality holds, the length is always positive. And this last point, when you take a symmetry and do it n times, the length exactly multiplies by n. That last problem, the last one is the problem. Without the last one, many examples exist. There you can talk of lengths on various symmetry groups. I'm not saying on every symmetry group, but on various symmetry groups, you can talk of lengths. But the last one is the really strange condition in some sense that, of course, it's very natural over the plane. You know, if you take a vector and double it, you can double the length. But in general symmetry groups, it's not clear. It was not clear. And that was the problem. So I emailed lots of people, as I said, in various places, also here. And eventually, after all those emailings, no such examples were found. Nobody could give me an example of a group which is not commutative, which is not abelian, but has a norm function. And no such theorem was known that such a group cannot exist. So it has to be one or the other. Either no such group exists, or you have to give me an example of such a group. So which is it? So, sorry, let's see. So yeah, so that's the point. And the question was now, which one is it? So, and the point is that it's hard. So, okay, if one can find an example of a group, then that's fine. You find something, you check that it satisfies these properties, you are good. But nothing was being found. And so then you have to try to show. And proving things are always hard because, you know, you have to come up with a statement that holds for every single case that anybody could consider. Maybe your imagination is not strong enough to consider all the possible cases. You can check in all the cases that you know that things work out or don't work out. But it has to be something that nobody else can also disprove. Anybody can think of anything and yet your method works. Yes. No restrictions. You are free to find any group, but it has to be not abelian and has to have a norm. No restrictions. Good. So yes. So immediately you can start discounting some things, like it cannot be finite. Why cannot it be finite? Because just think of, for example, is there a clock here? There is no clock. Okay. No, not the digital clock. I want an analog clock. So think of the clock, for example. Think of rotation by 90 degrees, 15 minutes past. That's a symmetry of the circle group or of the whole plane. Now, if the circle group had a norm, if it had a norm, then this thing is not, this is not the identity symmetry because it is taking 12 o'clock to 3 o'clock. So it has to have what can you say about its length? The length has to be positive because for all non-identity transformations, all non-identity, the first bullet point says that the length of the rotation by length of 15 minutes has to be positive. Then what does it say about length of 30? Suppose the length of 15 minutes is 2. Then what is the length of 30-minute rotation? 4, because of the third condition. If I apply this transformation 2 times, then I get twice the length. So if the length was anything positive, let's say 2 for fun, this would be 4, 45 degrees would be 6, and 60 degrees would be 8. So the length of rotating by the full hour would be 8. But what is rotating by the full hour is the trivial transformation. Because we didn't do anything. If you rotate by 360 degrees, you take the entire plane back to itself. You fix every point. So if 15 minutes had a length, then 60 minutes would have 4 times that length. And yet 60 minutes is 0 length because that's the first bullet point again. The identity transformation is 0 length. So the original length had to be 0, but that rotation was non-trivial. So it has to have positive length. So how can the positive length equal 0 length? So the only way is length cannot happen. There is no length function which satisfies the third property. Without the third property, you could maybe do something. With the third property, you cannot do anything. There is no length function on the clock because the 15-minute rotation cannot have a length. The 10-minute rotation cannot have a length. No, any integer factor cannot have a length. So you can start discounting some obvious groups. Any group where you have even one element, one symmetry with finite order, meaning you do it finitely many times, you get to identity element. That cannot have a length because of the argument I just told you. 15 minutes applies to 10 minutes, applies to anything. Anything which you do finitely many times and get to the identity, then the left-hand side would be the norm of the identity, which is 0. The right-hand side would be n times the norm of a non-zero element. And that would be a problem. So this the existence of elements of finite order is called torsion elements. And so torsion free is the groups which have nothing of finite order, except of course the identity transformation is of finite order. You apply it once, you get the identity. Apart from the identity, there are no other elements of finite order. That's what the word torsion free means. Okay, so so fine. So before I get there, maybe I should say something about proofs, right? So the nature of finding an example is always easy. You know, like if I say, I was just messaged on WhatsApp a puzzle yesterday, supposedly due to Martin Gardner. You get a 4x4 part of a chessboard, 416 squares. Can you place a queen, a king, a rook, a bishop, and a knight on this square, 4x4, such that the pieces never kill each other? No piece can kill each other. Okay, so they were all these black pieces. So of course, somebody gave the joke that they're all black pieces. They can't kill each other because they are in the same side. But let's assume that's not the point. So then finding a configuration is maybe, you play around with finitely many possibilities, and then you check and maybe it works out. But suppose this was not possible, I'm not telling you the answer. Feel free to go home and try it out. So try to find a configuration that works. But if you can't, after enough trying, then you have to try and prove that it doesn't work. And that means you have to try and say that all possible cases I consider will not work. Otherwise, you find one possible configuration that works. So that becomes harder because you have to consider all possible cases and make sure your imagination is vivid enough to consider all possible cases and check that it doesn't work. So prove that such a group can never exist. So just to give you a small flavor of this, just to tell you, let's see. So for example, I can say that this is a magic trick you can tell at a party, for example, kind of thing, is if I take two consecutive odd numbers, whichever ones you want, multiply them and add 1. And magic, you will get a perfect square. Now you can check this. You can check with 1 by 1. Like 3 times 5 is 15 plus 1 is 16. Yes, that's a square. 7 times 9 is 63 plus 1 is 64. That's a square. But that is not called proving it. You have to prove it for all possible cases, meaning at least you have to check it for all possible cases. How do you check? There are infinitely many odd numbers. How do you check infinitely many statements in finite time? You can't do it step by 3 times 5 plus 1, 5 times 7 plus 1, 7 times. You can't keep going down because that takes infinite time. So that's when you need to use extra tools. And the tool that one uses is called a variable. And then what you say is, well, let's take the middle number and call that n. Now you take n minus 1 is the first number, odd number. The second odd number would be n plus 1. And you multiply those and you add 1. And then you do the calculation as if these n were actually integers and you know distributive law and additive law. And when you do this calculation, you check that this is n square minus n plus n minus 1 plus 1. And then you start cancelling things out and you get x. And so in one calculation, you have proved or you have verified. Now, if I set n equals to 4, I get 3 times 5. If I set n equals to 8, I get 7 times 9. And in every case, I not only get that it's a perfect square, I get that it's a perfect square of the number in between those two odd numbers. So already this method of proof in one line verifies everything and also gives you more information. It tells you whose square it is. And it also tells you that there was no reason to assume two odd numbers. I could have taken two even numbers also. All I need is two numbers that differ by 2. It doesn't make use of any odd or even or anything. So sometimes proofs can be very powerful in that, of course, they prove infinitely many statements in finite time, but they also reveal more information than what your original problem may have told you. Anyway, so the point was find a proof that covers all possible cases. So somehow. Fine. So then this is where the problem was stuck for 2 years or maybe 3 years, because in December of 2017, very late, I went to UCLA in America, in California, and visited a collaborator. And this is a very famous mathematician, maybe one of the most famous mathematicians in the world, because of course he has done a lot of amazing mathematics and proved many amazing results and so on. He's won the Fields Medal and lots of other awards. But he also has a very popular blog, which many people read, even from undergraduates all the way to professors and so on. So I visited him for a different reason, which that reason didn't work out, but at least this problem got discussed. So I'm able to stand here and tell you about this problem today. And the discussion was the following. So now remember the question: can one find a non-abelian group with a norm function? So it's a length which is always positive, triangle inequality, and the scaling type. So, okay, I'm pretty sure I don't have time to do this blue part, so let's forget about it. Suppose G is any group with a norm, okay? I want to show that it's abelian. Suppose I want to show it's abelian. That was the goal. So, he said, well, maybe one can try to find some example, but he thought about it, I had thought about it, it didn't seem to work out. So I said, let's try to at least devise a strategy by which you could find a proof. Maybe the strategy doesn't work, maybe it does, but here is the strategy. Take any two elements, take any two symmetries, elements in the group, and the key quantity, which I will, for obvious reasons, call KQ, to understand is remember there was this commutator that we had called, so take the norm, take the length of that commutator, meaning the distance from the identity transformation in some norm. So what you are given a group with a norm, suppose you have one, then you have the norm of every symmetry element. The commutator is a symmetry element because you compose 4 symmetries. Take the key quantity. The claim is if this quantity is 0 for all symmetries. So when is this quantity 0? When is the length of anything 0? The length of anything is 0 if that thing is the origin, the identity transformation. When is the commutator equal to identity? That was the old calculation we saw. If and only if alpha beta equals beta alpha. If and only if. So only way this can be true is if alpha and beta commute. The only way that norm is 0 is if this is true. So the only way that norm is 0 is if alpha and beta commute. If you can show that this commutator is always 0 for all choices of symmetries alpha and beta, then your group is abelian. So that was the strategy. Okay, so once again, if the key quantity is the length of the commutator, so that is 0 for all symmetries, if and only if this equation holds for all symmetries, all pairs of symmetries, this equation holds if and only if alpha and beta commute. In that picture there. Yeah. The question is, what is the length function? The length of the word in the minimal form or something. In the free group, yes. Well, I can tell you the theorem, so I can talk to you later about why probably the theorem, what would go wrong in it, but yeah. But the answer is, yeah, it doesn't work. So now if you want to show something is 0, how do you show something is 0? There are 2 ways. One is algebraic, you do some exact calculations and show 0. But the other is using error estimates. And Tao was an analyst, so he likes error estimates. So the idea there is, this is a very old, this is named after a very old Greek person, I think, called, what's it called, this property? So a real number is 0 if it is less equals every positive real number. Archimedean property of real numbers, yes, Archimedes. It was not Diophantus. I was somehow thinking Diophantus. The Archimedean property of real numbers says that if some number x is less than half, 1/3, 1/4, 1/5, 1/6, and every 1 over n, then that number x cannot be positive. It is 0 or it is negative. So the point is, when you ask as basic question as this, you have a group with a norm. You don't have any continuous groups. You have no Lie groups, no symmetries like that. You can't use differentiable manifolds to play around. You can't use Silo theorems or something like that. I don't know what the group is. I don't know what the length function is. I just know that there exists one. So I have to use very basic, the foundational properties of real numbers, like the Archimedean property, like the triangle law, like the fact that multiplication is associative. These are the things one has to. Okay? So can one show that this quantity is very small, meaning can one bring down this estimate all the way to 0? Can you show that KQ is less than 1, less than, or maybe less than 5, or less than 3, or less than half? Okay, so we want to show this is the point we want to show by the Archimedean property, that the length of some commutator. So you fix two symmetries in the group, and then you worry about the length of that commutator and show it 0. So you want to show that number is less than epsilon for every positive scalar epsilon. You can also take 1 over n if you want. I don't need to show it for every real number, just 1, 1/2, 1/3. So first of all, if I have a length function, if I have a ruler by which to measure lengths, I can change the 1 centimeter to like 1 millimeter, and I would still have a valid ruler. The ruler itself, the lengths are different, but the fact that it's a length function doesn't change. The triangle inequality still holds. You would just multiply all the lengths by 1/10. The norm condition still holds. You would multiply both sides by 1/10, etc. Right? The positivity doesn't change. If you multiply a positive number by 1/10, it stays positive. So first of all, you can normalize or you rescale the number so that all these 4 lengths, because these are the 4 symmetries involved, so make all of their lengths less than 1, let's say. So what can you say then about the length of that red thing? What can you say about KQ? If all those lengths are less than 1, then what can you say about the key quantity? So I have something like this, whatever. At the most, the length is less than the length of this plus length of this plus length of this plus length. That's the triangle inequality, right? So at the very least, I have an upper bound of 4. This is without anything, just from the definitions. But now I'm going to start getting slightly cleverer. Okay? I'm going to tell you that this is just obvious. If you have a group with a norm, I get 4, but I actually get 2. And for 2, I need this point, that if I do something called a conjugation of a group, then that does not change the length. Okay? So if you knew this fact, can you tell me why the key quantity is bounded above by 2? The key quantity is the norm of the thing in red at the top. The first 3. That's right. So all you do is you just break it at the last circle, or maybe the first circle, either way. So yeah. So this is composing this symmetry and this overall symmetry here. Now the overall symmetry here has some length and this symmetry has a length. So this length is less than that. But if you believe that, if I can prove that conjugation doesn't change the length, then this is exactly equal. This is equal, and now this is 1 plus 1, so I get 2. So if I knew some extra facts, then I could be cleverer. But of course, I don't know this directly. But the point is, you can prove it. Just like you can prove something exactly for all possible cases, we can prove that the conjugation does not change the length, just using the norm property and the triangle inequality. So I will, if I have time, I'll tell you that. Let's see. And now I'm going to tell you that we can actually improve it from 4 to 2 to 4/3. So now you have to start playing these cleverer and cleverer tricks. Like one trick right now was break it here. Don't break it at all 3 places, just break it here. And use the fact that conjugation works. Okay? So how does one do 4/3? So how do you show that a number is less than 4/3? One way is to say you say 3 times the number is less than 4. Fine. What is 3 times the number? What is 3 times the length of something? Times norm of whatever. We know that this is the norm property, that 3 times the norm of something is the same as the norm of that thing. If you apply this symmetry to the system 3 times, then the length triples. That is the defining property of the norm, right? So that's what we did. So you want to show this thing, and what you do is the following. Now you use the fact that when you come, so 3 times this is the norm of 3 4-length strings. But I can say that applying 12 transformations 4 at a time is the same as applying the same 12 transformations 3 at a time, because that's what is called the associative law. It doesn't matter in which order you start applying these transformations, as long as you're applying them in the same sequential order. Whether you clump them into 4s or you clump them into 3s, doesn't matter. So that's the associative law. And now we are done, right? Because each of these guys is a conjugate, meaning something times some other thing times the first thing inverse. And so now by the triangle inequality, by subadditivity, this is just less than, the first one is, the length of the first triple is just the length of beta, the length of the second triple is length of alpha. And so you get 1 plus 1 plus 1 plus 1 is 4. So you have to start being cleverer and cleverer about these things. And once you do, you can get from 4 to 2 to 4/3. But the question really is, we need to bound this all the way to 0. And that is much harder than, these are very simple tricks. How do you get from 4 to 2 to 4/3 to 0? Fine. So this was when, this is the point at which we stopped discussing. Yeah, as the title of the slide says. And then I left, and then Tao asked me that night, can I put this on my blog? Of course, it was a very famous blog, so who's going to say no to getting your name on Terry Tao's blog? So I said, of course, please go ahead. So he did, and here is a curious question posed to me by Apurva Khare that I don't know the answer to. And then he explains all these things, and below the fold is where the previous calculation was. And then he says, what is not clear is if one can keep arguing like this to continually improve that upper bound all the way to where the upper bound would be 0, would must in fact vanish. Anyway, this feels like a problem that might be receptive to a crowdsourced attack. So here it is. And then, as you can see, there are various comments on this thing. But yeah, so what happened is then I took the 17-hour flight from San Francisco. I flew to San Francisco and then took the 17-hour Air India flight to Delhi. And when this was posted just, I think, before I left, by the time I landed, there were so many comments and lots of ideas. So now I want to tell you about, as I said, not just the theorem or the result itself, but the timeline. Because as I told you, it got done in 5 days after being 2 years of no progress. So fine. In the first one, he already wrote those estimates that I told you, 4, 2, and 4/3. The first comment that came, the first non-trivial comment maybe, the progress was 3 hours later by somebody sitting in Germany. And that was that if it is a norm, then indeed that conjugation invariance holds. So I told you that once you have conjugation invariance, then you can do 4, 2, and 4/3. So, but why is that true? So we had assumed it, but he said, you don't need to assume it. Directly you get it. So why do you get it? Let's see. Okay, fine. I'll take a little more time. So here is the idea. It's a very cute idea. It's a very clever idea. The idea is very simple. Take some integer and multiply it by the norm of the conjugate. You want to show that the left-hand side is equal to norm of h, right-hand side. So multiply left-hand side by n. And what do we know? We know that G inverse norm times n is exactly the nth power norm. Right? So, and now this is a trick that you might have seen before. If I multiply G inverse, G inverse, G inverse, what happens? Well, this and this cancel. This and this cancel. So inside the G and the G inverse on the outside, I just get H. So the G inverse and G start cancelling away. Now the same thing happens if you multiply 3 times or if you multiply n times. There is no difference. So that's the last equality here. Right? This one. So, and now because we know that the length is subadditive, therefore this length is less than G plus G inverse plus n. That's all. That's it. So the n times that length is less than these 3 things. And now divide by n. What do you get? You get this length is less than n cancels and some error term divided by n. So now if you let n go to infinity, which is another standard tool you can use, taking limits. So Archimedean property, what was it? Associative law, taking limits, very, very fundamental notions that we see in college, if you will, or maybe high school. Now, when you take limits, then you get one inequality. The length of any conjugate is less than the length of h. But this guy is a conjugate of this. Similarly, this is a conjugate of that. I can pre-multiply by G inverse and post-multiply by G, and those would cancel. So if you think of it, conjugation is a symmetric relation. So under that symmetry, I get the other way around. And so that's why you get equality. So this is how you start proving basic things. So this was his 4-line proof 3 hours after he posted the blog. So that at least justified our estimates of 4, 2, and 4/3. We did not need to assume conjugate invariance. This was proved. Fine. And then 2 days were spent out of those 5 in trying to understand, let's just find an example. As I said, proving things is much harder. Let's just find an example and we are done. Here is an example of a group that's not abelian, but here is a norm on it. Did not work. People tried all kinds of crazy techniques and amazing things and nothing worked. Then they said, okay, fine, let's start to maybe improve from 4 to 2 to 4/3. Let's try to bring that down to 0. Let's maybe there is a hope. So then there was some 5/4 that worked. Somebody did something even more clever, not just this conjugate invariance and breaking groups of 4 into groups of 3, but something even crazier. Look at the progress though. 4/3 to 5/4 is improvement of 1/12. Now from 5/4 to 1916 is the improvement of 116. So it wasn't really getting very close to 0. Forget 0, it wasn't even crossing 1. You have to first go down below 1, then you worry about half, then 1/3. Finally, at some point, somebody did something which is just so hopelessly clever that and complicated that I have no hope in heaven of understanding it probably. Anyway, I don't understand, but I didn't look for it actively. But finally, it went below 1. So the length, what was this? Remember, the key quantity was the length of a commutator. We have to show that this number is 0 or less than every positive number. Then if it is 0, then these guys commute. If these guys commute, this is identity, so these guys commute. And we are done. And this will keep happening again. Okay, fine. And at this point, so among the 5 days, 2 days were spent in trying to find examples that didn't work. 1 more day was spent in trying to improve this, and that didn't work. So the 3 of those 5 days were really no progress, but that was important in understanding the remaining, appreciating the progress that was made. So this is another thing about research, right? We spend so much time in the failure part, or well, maybe the correct thing that I think my advisor told me or somebody in grad school was, behind every theorem you prove are at least 3 attempts, 3 unsuccessful ways of proving that theorem. And the same thing, behind enormous progress lies enormous failures as well, right? I think somebody once said, I forget who, that I regard each failure as a, what was it? Have you said, I regard each failure as a way to teach me what not to do or something like that. Anyway, so people tried really hard to come up with more crazy, clever word games of that kind, but it didn't work. And that takes me to the last modern aspect of this collaboration. It was done on a blog. All these things were being done on Terence Tau's blog in the comment section. It was done on a blog. It was done by people who had never met each other. And there was a computer involved. And now this is where a computer helped us prove something or make the next progress, which was not done before that. So Siddharth Gadgil, who is my colleague at IISc, he had started programming his computer from the very beginning to look for a proof to improve the bound. And he was himself humanly working by himself to find a counterexample. So he was simultaneously attacking it in both ways. Now that takes really, like imagination, that I don't care which way it is. I will do both ways together. So he launched this computer to search, I think like 4:500 searches in these 3 days that happened. And he himself tried. He could not work because it did not work out. But the computer managed to find a breakthrough. He programmed the computer to write down that proof. This implies this, implies this, implies this. And it took 126 lines of proof. So human beings would not have been able to come up with it, probably. But it took 126 lines. And the computer finally improved it from 22/23, which is 0.95, to 0.816. And at that time, when he announced this is the comment on Terence Tau's blog. One can get a brutal bound on the commutator with a brutal proof. Blah, blah. Here is the link. That is the link to this page. Comments welcome. And someone called Pace Nielsen was sitting on a Friday night in Utah after dinner at his laptop for some reason. Maybe it was very cold. It was very cold in Utah. Maybe that's why. He was home for the holidays near Christmas. So he looked at that. That was at 8 p.m. on Terence Tau's time, UCLA time. Exactly 100 minutes later, Pace Nielsen announces, this was beautiful. I looked through your file. The first 40 lines do this. The next 30 lines do this. The next 20. So in 100 minutes, he read 126 lines of code, completely understood what it was doing, and then says, this was very well done. And here is how to improve this. He started improving it in 100 minutes also. So there are some very, very clever people out there who take a look and they understand it in one reading, maybe, I don't know, and then they think. And then he posted all this. He wrote all this up with LaTeX and whatever in 100 minutes. Then other people took over, and then this was isolated into some actual result. This is the principle that is underlying the proof that Siddharth Gadgil's computer gave, and then Pace Nielsen improved. So this was changed into this proof, which I don't have time to get into. But the point is, as a sample application of this one lemma, okay, so this is some nice lemma, which works for every group with a norm. I won't tell you the lemma or its proof, but as a sample application, one immediately gets 8/11. And 8/11 already blows out the previous best world record. The world record was 816. This is 0.72. So just on this one screen, using the previous lemma, I can blow it off. But now even still, fine. You get from 4 to 2 to 4/3 to whatever to 816 to 72. You want to get all the way down to 0. If you think logarithmically, let's say below 1 means log is negative. So you get from some number with a negative log to another number with a more negative log. But you want to go all the way down to 0, whose log is minus infinity. So making finite logarithmic improvements is not going to help you go down to minus infinity in finite amount of time. You have to verify you have to do infinitely many steps in one go or in a finite amount of time. So how do you do that? Luckily, it turns out that to show this is in fact 0, it goes down all the way to 0. That lemma that I skipped over just now, because that's a technical lemma, but you have to use it a large number of times. You have to use the lemma billion times. You have to use the lemma 10 billion times. You have to use the lemma infinitely often. If you can do that cleverly, that actually does the job. And at the final step, when you write down the proof at the final step, you can use either combinatorics in some way or just binomial random variables or Bernoulli random variables. And in that case, if maybe some of you might have seen this thing, there is this underlying principle that if you take one random variable and add it to itself, x plus x plus x 3 times, the variance of that is 3 square. If you take 3 random variables which are independent with the same distribution, x1 plus x2 plus x3, the variance of that is no longer 3 square, it is 3. So the moment you have what one calls IID, independent and identically distributed random variables, the variance does not become square, the variance stays linear. And that was the trick. For that, we could use that to somehow say that this, whatever this is, it's growing slower than something which goes to 0. So it must be 0 itself. So eventually we started with this metrics and lengths in geometry, groups in algebra, using error bounds and some length is less than something like analysis. And finally, we use some probability as well. So really this proof is, this result itself is somehow a slogan of the unity of mathematics, that in all these algebra, geometry, they all look different and different people may believe that you have to hate at least one of them to, do a good math something. But really sometimes they can be one and the same thing. So it might actually be, useful to know all of them and don't hate all of them. Anyway, but this was first observed on this by Terry Tao at some point, and that finished the proof. So just to say the final steps of the proof, what happened is first that 22 or 23, then there was a 1-day break when Siddharth's computer broke through. Then after that, then that lemma that was isolated helped us reduce it to 0.72. Using that lemma further, somebody did 0.6. And then Tobias Fritz, the guy who first suggested conjugation invariance, got another clever idea. And using this kind of discrete heat equation kind of thing, Terence Tao finally finished the proof. I think this does indeed work to give arbitrarily small bounds on the commutator using some fancy thing in probability called Chernoff bounds, which we later reduced to something much simpler called the Cauchy-Schwarz inequality. So it really doesn't need any hi-fi Chernoff bound, just Cauchy-Schwarz, which people know. Cosine is less than 1, and dot product is less than norms. And so the final theorem then is that G is a group. Any group, no restriction, finite, infinite, continuous, discrete, doesn't matter. G has a norm if and only if G is abelian and the torsion free, which is the part that there are no 15-minute rotations, no elements of finite order. That's it, if and only. If and only if, and any such group with a norm, obviously, embeds inside something called a Banach space, meaning it basically embeds inside R2 or R3. So the punchline of the talk is that this was what we call an example, but basically it is the only example of a group with a norm. The ones that we started out with are the only ones. There's nothing else possible. It has to be a subgroup of a Banach space, of a vector space with a norm, Rn, R infinity. So then we wrote a paper about this, and the paper appeared. There was some blog which said spontaneous Polymath 14, a success. So there is this this kind of collaboration mechanism which happens on the blog and involves either Terence Tao or Gowers or both of them or Gil Kalai. These are these Polymath projects, and this became a spontaneous Polymath project. And there is a list of all these kind of when we finally wrote this up. This was the latest, but as you can see, there are lots of previous Polymath projects. Some, like Polymath 12, proving Rota's conjecture, proposed here, no resolution. intransitive dice proposed here, no resolution. So there are several Polymath projects, not all of them are successful. This one was completely sort of a spontaneous one, but luckily it worked out. So that was a nice pleasing end. These are the papers that have come out of the Polymath projects. By convention, it has been decided to call the author DHJ Polymath. There is a reason for the very first one, this one. This is the D, the H, and the J, density Hales-Jewett. And yeah, so that's about it. But basically, so what started out as a search for more and more clever tricks, to reduce this bound on that norm of the commutator, the key quantity, ended up as a collaboration, like 5 days, out of which 3 were basically inaction. Well, not inaction, unproductive to whatever extent. And but involved 6 people, at least 6 people. Several others also contributed comments. And it crucially involved a computer-assisted proof. It happened entirely on the blog, and it led to sort of characterizing the very first thing one sees in the math major program, which is groups, abelian groups. But it led to characterizing abelian groups using analysis. We never see analysis in an algebra class, but maybe we should, because, well, a group is abelian and torsion-free if and only if it has a norm which comes from analysis. Okay, I think I'll stop here.
Fantastic, Professor. Terence is such a great. Yeah, please it's open for questions now. Just hold on.
How do you give instructions to computer to get some mathematical proofs?
Yeah, so that's a very good question to which I don't know the answer. But there are these, so Siddharth Gadgil definitely was very well versed in programming computers. And there is even now something called automated theorem proving. So you enter a proof. You can, first of all, there is, you can write down proofs using, logical quantifiers. There exists, for all, implies, such things. So you can write down mathematical language in using logical symbols. In fact, Bertrand Russell had this idea, a grand program to write an entire book which proves all of mathematics, starting from the scratch using this. So he should write it in logical language also, until Gödel's incompleteness theorem destroyed that ambition. But the language exists. So once the language exists, you can enter language in some syntax way into a computer. So there are programs or things that check, you can enter a proof in the library. So they have some previous things, like once the set of primes is infinite. That has been, there is agreed upon, there's a standard proof of that. So that's one of the libraries in that software called Lean, for example. Then the set of composite numbers is infinite. That's there. So you can enter basic facts. Then you can enter a supposed proof. Is this proof correct? You enter that proof inside. So then the computer checks whether the proof is correct. I know that's not answering your question. That is proof checking, not coming up with the proof. But so similarly, it's possible to program a computer. Here are the rules you're allowed to play with. Here's a function. Here is a group with words in alpha, beta, alpha inverse, beta inverse. Look at all possible strings. Right? And the rules are alpha times alpha inverse is 1. So you can cancel it out. Alpha inverse times alpha is 1. You can cancel it out. Same for beta and beta inverse. Now, here is a function length, which also now has the fact that length of G at G inverse is length of H. Length is subadditive, and length is equal to. So you program these instructions in and you say, okay, look at the lengths of all possible words of a certain length or less. That's why I said 4 to the 500, because 4 generators, alpha, beta, alpha inverse. He looked at words of length 500 or less. So maybe it's more than 4 to the 500, it's 4 to the 500 plus 4 to the 499 plus 4 to the 498. So yes, so he did not go infinitely. The computer yielded, luckily, we were very lucky that there was a counterexample or example at length 500. If the first one was at length 5000, then we would have taken 1 year the computer might have taken 1 year before it gave out the first answer. So maybe if you have seen Avengers Endgame or something, then Dr. Strange says there is one future where we win out of 70 billion futures. So that was the first example the computer found after intensive calculations for 3 days. One example out of 30 billion or 30 million examples the computer looked at. But it may not have been the only one, it was the first one. And as soon as it found it, it told Siddharth, okay, example found, a proof found, estimate improved, whatever. And then it did. So basically, I think what he rather did was, he kept saying, do your calculations at each stage, remember what you have already done to get the bound on, what is the best bound using this data on the commutator length. Now using that, and then let me know, then he would program. Okay, now let me know when the length is crossed 0.816. That was the bound he wanted, or 0.92 or whatever. The moment it crossed it and it gave the first next answer at 0.816, he was happy and said, okay, tell me what this answer is. Write down the proof. How did you get this? Write down the proof. If it is possible for computers to check proofs, it's possible for computers to write proofs. That sounds even more believable. The computer followed a sequence of operations using the given data. So he asked it to write down what data it used in what order. It wrote it out, and then that's what he published. But for more details, email Siddharth Gadgil. He can probably tell you. I'm talking like a complete layman. I have no idea about programming. If you ask him, he will, I'm sure, be happy to. That was brute force. But then more intelligent brute force in the sense you remember what you have done already. So if you encounter a similar string and you remember that that string has already been done, like, after it's a length 500 thing, after maybe he has done 100 length string, the computer is doing some other thing where the first 50 are different, but then the string is the same 100 length string as here. Then it will just bypass that calculation because it has already done it. So some things you can help speed up by remembering things and then brute forcing. Don't think he used cluster time, but maybe I'm wrong. We do have a supercomputer. Maybe he used cluster time. I don't know. I thought it was only his laptop, but maybe I'm wrong. Yeah.
One question. So, suppose you take an infinite cyclic group, what kind of a norm would work for that?
Infinite cyclic group you can think of as the integers.
Yeah, but what norm? Because a norm has to be bounded, right?
No, I never said norm is bounded. Integers have a norm because they sit inside the real line, so the usual norm. In fact, the norm is the only norm that you have is the usual kind of norm. There is no other norm. That's the point. It's the only example.
Yes, Aveek, one.
Sorry. This was before. This is 2018. There was no chat GPT.
No chat GPT that time.
There was
Any
one
other-
person at the back. I think he had a question.
You had, oh, okay.
So Apurv, you said if you relax the last constraint about doing it
length
with
being
scalars or
scaling,
multiplying with scalars, then you can. So if you relax, what kind of either examples or interesting things can you?
That's the one he was saying. The free group you can find word
Free group
metrics.
you can find just word.
Basically, think of the shortest way that you can write down. So, in fact, even in a reflection group, like a coxeter group or something, you can talk about the length. The length of a word is the minimum number of reflections used to write that thing. Not just simple reflections, that is the usual length as we call it, but any kind of reflections, conjugates of reflections. That's also another length function.
Amul?
Very, very random thought. So in physics, for example, you have lots of quantities whose commutators are non-zero, right? Finite
Huh.
kind of thing. Maybe it's possible to use this theorem to show some no-go theorems in physics, which might look very trivial, but it's just nice to see because the proof was very beautiful.
The proof.
So even if we can make a not so deep statement in physics using this, it would be nice.
Yeah, definitely. I mean, so this is such a completely arbitrary problem in some sense, but eventually there are papers that actually cite this result in mathematics, in geometry, something called stable commutator length and so on in geometric group theory. So potentially, yeah, there should be applications outside of pure math as well, like in physics as well, for mathematical physics for sure.
Yeah, so often in physics, we express the action of the group on some vector space representation. And we are interested in the norms of those vectors. So having a norm on the group, does it say anything about the...
I mean, so orthogonal groups, we know that the action of orthogonal matrices preserves norm. In general, I'm not sure if... but yeah, maybe this kind of a group thing gives you... I mean, once it has a norm. Once you have a norm on the group, you know that it's only of this form. So then you are looking at representations of Rn, really. And that's abelian groups where representations are sort of very well understood. I think all characters are one-dimensional.
Right.
Complex representations, I would say, but maybe real representations are at most two-dimensional, irreducible ones or something. So those are maybe easy, already understood. Because once it has a norm, it's just Rn.
Right. Okay, thank you.
Okay, yeah, Arko.
It's a negative result in some sense. So I came to it from, we were trying to do something in probability theory, where we were, so there are things like central limit theorem or weak law of large numbers, which say that if you take some random variables and you take the average of them and take the limit, or divide by square root n for central limit theorem, then it converges exactly. It converges to the mean in almost surely for strong law of large numbers, or it converges to normal distribution, the Gaussian in distribution for central limit theorem. But then the modern day tradition has been that rather than do exact convergence, what does it converge to? You look at the tail sums. The remainder terms, what does that, can you put better and better bounds on them? Of course, if your bound goes to 0 asymptotically, that's exact convergence. But if your bound doesn't go to 0, can you at least put some better bounds than better and better bounds? So we were looking at doing such things for sums of variables which are not real valued, which are not Rn valued, which are group valued. And our groups are not abelian. But then what we proved in the second paper, so this is exactly here actually, here. So that was the paper number 3. That was where we looked at non-abelian group valued variables with a metric on them. So convergence, you can talk of reaching a limit. But in the second paper mentioned there, actually that's outdated, it's published now. We proved that if the group is abelian and has a norm, then you get some nicer things. If it is abelian and has a norm, it is nicer than the third paper. So I wanted to ask, okay, maybe only the norm condition is necessary. Why abelian? Maybe it's just the norm condition that's necessary, and then the nicer things also hold, better error estimates also hold. So then I wanted to find out, okay, let's try to prove it for non-abelian groups with a norm. And I couldn't do anything. So I said, okay, fine, let me find one example and then at least prove my probability results, better estimates hold for that example of a non-abelian group with a norm. And then I couldn't find any example of a non-abelian group with a norm. And then I emailed people, can you please give me a non-abelian group with a norm, because I want to prove these better estimates in there. But nobody could give me, and then that's how the story started. Oh, because, so that is a nice question. Correct. And the reason was because even in the non-abelian group with a norm, we were assuming the metric was left translation invariant and right translation invariant. So the moment you do both invariant, you need, that is the same as saying conjugation invariance of the norm. If it's only left invariant, it is the usual length function without conjugation invariance. But the norm properties can also guarantee the conjugation invariance or right translation. That was news to me because of Tobias Fritz.
Okay, great. So I think this is a very, very nice lecture. Thank you, Professor Kare. You really took us on a long journey. Let's thank him. Thanks for coming here. And please join us for high tea outside. And thank you, all of you, for coming here.
So please stop sharing. Me off karo. I'll turn this off. I will stop sharing.